This video goes along with modules 10 and 11. We are still working with Earth's systems and resources. So we will cover global wind patterns, Earth's geography and climate, and El Nino and La Nina today. Air has several important properties that determine how it circulates in the atmosphere. We will look at density, water vapor capacity, adiabatic cooling and heating, and latent heat release. Starting with density. Remember that density is the mass of all molecules in a given volume. Less dense air rises and denser air sinks. At constant atmospheric pressure, warmer air has a lower density. Moving on to water vapor capacity. Warmer air has a higher capacity for water vapor, so think about those hot, humid summer days. And the saturation point is the maximum amount of water vapor in the air at a given temperature, which does increase with temperature, as you can see from the graph on the right. Adiabatic cooling and heating is a response to changes in pressure. With cooling, we see a cooling effect of reduced pressure on air as it rises in the atmosphere and expands. Adiabatic heating is the heating effect of increased pressure on air as it sinks toward the surface of Earth and decreases its volume. And those will be important as we talk about how convection currents are. Finally, latent heat release is the production of heat when water vapor condenses from a gas to a liquid. Putting that all together gives us atmospheric convection currents, which are a major contributor to different climates on our Earth. Global patterns of air movement are initiated by the unequal heating of Earth that we talked about last time. They also involve the movement of air that absorbs and releases heat as air moves up into the atmosphere and then back to Earth. This is an example of how atmospheric currents develop. Starting at the very bottom, hot, dry air picks up moisture as it moves along the land's surface. Humid air at Earth's surface warms and rises. Then we have adiabatic cooling, which causes air to reach its saturation point, which leads to condensation, causes cloud formation, and we have some precipitation. Latent heat release from condensation causes air to expand and rise even higher. Then we have more adiabatic cooling that chills air at the top of the troposphere. That cold, dry air is displaced horizontally and sinks back to Earth's surface. Then we have adiabatic heating, which warms the dry air that sinks to the Earth's surface, and that happens over and over and over again. Atmospheric convection currents are found at specific locations. Hadley cells, which is what our example one will be, are found between the equator and 30 degrees north and south of the equator. Polar cells are between 60 degrees and 90 degrees, both north and south. And Ferrel cells are between Hadley and polar cells. So let's specifically look at what happens with a Hadley cell. First, at the ITCZ, which is the Intertropical Convergence Zone, the sun heats the moist tropical air, which causes it to rise. Then, the rising air experiences adiabatic cooling, which causes water vapor to condense into rain and fall back to Earth. The condensation of water vapor produces latent heat release. This causes the air to expand and rise farther up into the atmosphere. Then the warm, rising air displaces the cooler, drier air above it to the north and south. Then finally, the cool, dry air sinks and experiences adiabatic heating. It reaches Earth's surface as warm, dry air and then flows back towards the equator. So we have that sort of movement on both sides, to 30 degrees north and 30 degrees south from the equator. Earth's rotation causes the Coriolis effect, which is the deflection of an object's path due to Earth's rotation. So what you can see on diagrams A and B, that the dashed black line is what we would expect to happen if we were throwing an object, for example. But the red path shows the deflection of that object because of Earth's rotation. So in diagram A, from that direction of rotation, the ball is deflected westward when it is flown or thrown from the North Pole. And we will look at lots of specific examples with this in class. Moving on to prevailing wind patterns are due to atmospheric convection currents and the Coriolis effect. So you might notice our prevailing winds. Those wind patterns on this globe picture here to the right does show the same direction as the, if we were throwing a ball with the Coriolis effect. And then you can see the placement of the atmospheric convection currents. Hadley cells closest to the equator, followed by Ferrel and then polar cells. The rain shadow effect causes mountains to be dry on one side. So rain shadow is the region with dry conditions found on the leeward side of a mountain range, and it's the result of humid winds from the ocean causing precipitation on the windward side. So then we have that cooler, dry air for the other side of the mountain only. Surface ocean currents move warm and cold water around the globe. The flow of ocean water is also an important factor for global climates. The ocean current does affect primary productivity, and they are driven by temperature, gravity, prevailing winds, the Coriolis effect, salinity, and the locations of continents. Gyre is large-scale water circulation. It is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Upwelling is the upward movement of ocean water towards the surface because of those diverging currents. So this is ocean currents on our globe. Those darker blue spots are the upwelling zones. So you can see we've got several of those around the globe. And then you can see the direction of the ocean, which again is a combination of temperature, salinity, where the continents are, and the Coriolis effect. We also need to look at thermohaline circulation, which are the oceanic circulation pattern that drives the mixing of surface water and deep water. So starting at place number 1 over here, which is relatively close to the east coast of the United States, maybe Florida-ish. Warm water flows from the Gulf of Mexico to the North Atlantic, where some of it freezes and evaporates. The remaining water, which is now saltier and denser, sinks to the ocean bottom. The cold water travels along the ocean floor, connecting the world's oceans, and the cold, deep water eventually rises to the surface and circulates back to the North Atlantic. So that is the path of thermohaline circulation. An issue here is that climate change can affect thermohaline circulation due to melting glaciers, which will decrease the overall salinity, which can, have some problems there because it's not able to rise back to the surface. Finally, we will look at El Niño Southern Oscillation, or ENSO, which is caused by a shift in ocean currents. ENSO is a reversal of wind and water currents in the South Pacific that occurs every 3 to 7 years, and it begins around December 25th, which is why it is called El Niño. The trade winds that normally blow from South America and push surface waters to the west will weaken or reverse direction. This change in winds allows warm water around the equator from the western Pacific to move eastward. The movement of warm water and air towards South America suppresses upwelling off the coast of Peru. It's always one of our upwelling zones. It can last a few weeks or a few years. ENSO does decrease productivity and fish populations. It also leads to cooler and wetter conditions in the southeastern United States, where we live, and drier weather in southern Africa and Southeast Asia. So on this diagram at the top in figure A, we can see what things look like in a normal year. We have our trade winds, surface water, and where our cold, deep water is going. But in an El Nino year, we have that shift in direction of both wind and ocean currents.